Welcome to this lecture video of Aatablemultivibrator multivibrator using 555 timer. In the previous lecture, that is in the part A, we have discussed about the pin diagram and the block diagram of IC 555, and in this section we will be discussing about the Aatablemultivibrator multivibrator. Now, what is a multivibrator? A multivibrator is a circuit whose output changes between two digital levels, and there are basically three types. One is astable, then monostable, and bistable. Astable, it has no stable state. Monostable has only one stable state, and bistable has two stable states. Now here is the details. In the Aatablemultivibrator multivibrator, say there is minus V out and plus V out. It will oscillate between these two at a particular time period. It has a particular frequency, and that is determined by the external RC circuit, and it has no input signal. This point should be clearly understood. Now next point is monostable multivibrator. In the monostable multivibrator, there is one stable state, and here the stable state is minus V out, and when some input signal is given a time interval t1, it will go to state plus V out, that is unstable state, and it will stay there for some time, and it will again come back to stable state after that certain time, and that time is determined by the external RC circuit. Now here is the bistable multivibrator. In the bistable multivibrator, there is two stable state. One is minus V out and another is plus V out. In the minus V out, when some input is given at T1, some trigger is given at T1, it will jump to plus V out stage, and when some input is given at some T2, it will again come back to minus V out state. So this is bistable multivibrator. Now here we will see what we have done to make IC 555 timer run as Aatablemultivibrator multivibrator. Now here it is the block diagram of the Aatablemultivibrator of IC 555 timer. Now here number 1 pin is the ground pin, it is connected to the ground. Number 8 pin is the VCC pin, it is connected to the VCC. The number 4th pin is the reset pin, it is connected to the VCC to prevent it from accidental reset. The pin 6 and 2, these two are connected together, and it is connected to this point. It will get the capacitor voltage all the time when it is running. Now the discharge pin, it is connected in this junction, that is between R1 and R2. This capacitor, it will discharge through this point, through this discharge transistor. Now here is the control pin. The control voltage applied at the pin 5 will change the threshold voltage level, but for normal use, pin 5 is connected to ground via this capacitor 0.01 microfarad, so the external noise from the terminal is filtered out. Okay, now we will discuss about the operation. Now the following schematic describes the operation of the IC 555 as a stable multivibrator mode. Now look, first we should look what is the output. This is the output voltage waveform that we will get from the pin 3. We will get a square voltage, this is like waveform, and this charging and discharging pattern of the capacitor we will discuss here. Now initially, when the power is just switched on, the flip-flop is at a reset condition, and hence the output of this flip-flop, it is at reset. That means the Q will be 0 and Q bar will be 1. If Q bar will 1, that means it is a inverted output. Here is a NOT gate is here, so this output will be 0. Initially it is 0. Now if Q bar is equal to 1, that means this is already connected to the base of the transistor, this one. So if this is 1, that means the transistor, it will be switched on, it will be driven to saturation. That means if this is turned on, then if the capacitor voltage is capacitor is charged initially, then the capacitor will discharge through this path. Now when it is discharging through this path and the voltage across the capacitor comes below 1/3 VCC, okay, when the voltage below the of the capacitor comes below 1/3 VCC, then what will happen? This comparator comes into the picture. Now look at the voltage of this comparator at this non-inverting terminal, the voltage is 1/3 VCC. When this voltage at terminal 2 comes below 1/3 VCC, that means the non-inverting input terminal voltage is greater than inverting input terminal voltage. So this will be high. I am denoting high by H. So when it is high, this H high, that means that SR flip-flop, the flip-flop will be set at S is high. So it will set means the Q will be 1 and Q bar will be 0. And when Q bar is 0, that means this BJT base is 0. That means this BJT will be turned off. And when this BJT is turned off, that means discharging path is now closed. Now from this time, this capacitor will charge through this path. The capacitor will charge through R1 and R2 resistance. Now for notice carefully, when it is charging through R1 and R2. When it was discharging through this path, and it was discharging through R2. Now what will happen? Now when it is charging through this path, this voltage of the capacitor will increase exponentially towards VCC. Now when the voltage of this capacitor reach 2/3 of VCC and tries to cover 2/3 VCC, what will happen? Now look carefully, this comparator 1. What is the voltage here? Here the voltage is 2/3 of VCC, and the other terminal voltage, it is connected here. When this voltage is greater than 2/3 VCC, then this comparator 1, it will come into action. The non-inverting terminal voltage, it will be greater than inverting input terminal voltage if this node voltage goes beyond 2/3 VCC. So for that case, it will now become high. That means the reset pin of this flip-flop will be high. That means again this Q will be 0 and Q bar will be 1. Again Q bar 1 means what will be the output? Here the output will be 0. So what was initially, it was 0. Then when the flip-flop was set, it was when the flip-flop was set, the output from the pin 3 was like this, and when it is again reset, the output will be like this. Now when the flip-flop is reset, the Q bar is equal to 1. That means this is again 1. That means the transistor is again switched on. This is 1. The transistor is again switched on. That means the capacitor will now discharge through this path. It will discharge through R2 path. Now what is happening? Just we check the output waveform. From 1/3 VCC, the capacitor is charging. That means the capacitor is charging. That means this is charging through this path. So this is charging through this path, and this is charging through R1 plus R2, this two resistance, and it is reaching up to 2/3 VCC. When the capacitor voltage has reached up to 2/3 of VCC, the comparator 1, that is the comparator here, this comparator, the comparator 1, it will come into picture, and it will change the state of this flip-flop, and this Q bar will be 0 and this transistor will be turned off, which will make the transistor switch off, and it will the capacitor will discharge up to 1/3 of VCC, and it will go on and on. So when the capacitor is charging, capacitor is charging, because this Q bar is equal to 0. That means here the output is 1. Then we are getting this high value at the output, and when the capacitor is discharging, that means when the Q bar is equal to 1, that means when the capacitor is discharging, then when it is 1, then the output is 0. Then we are getting this portion. So we are getting like this waveform. We are getting like this waveform. So up to T on, this capacitor is charging. For this portion, the capacitor is discharging. Now we will calculate the charging and discharging time, and from that we can calculate the duty cycle. Now for simple circuit theory formula, for a capacitor voltage, VCC will be VC will be equal to VCC into 1 minus e to the power minus T1 by RC. RC is the time constant. Now T1 is equal to time taken to reach 2/3 of VCC when capacitor is initially discharged. So from initial 0 voltage to reach 2/3 of VCC, it will take T1 equal to 1.09 RC, this amount of time. The calculation is very much simple. You cancel the VCC and VCC. You just 1 minus, you just bring e to the power minus T1 by RC1 to left hand side and 2/3 to that right hand side. Just simple calculation. Take logarithm of e base, and you can from that you can simply find this value. Now consider this case when it is the time required to reach 1/3 of VCC. Simple, you can calculate this, and it will be T2 will be 0.405 RC. Now what is T on time? T on time is the time that is required by the required to reach from 1/3 VCC to 2/3 VCC. That is the actual T on. That means we have to minus we have to take T1 minus of T2, so that is T on. So what is the value? T1 is 0.69 RC. Now look carefully here. R is not a single resistance. Here when the capacitor is charging, it is charging through R1 and R2. So here R is equal to R1 plus R2. Now for discharging, look at this side. Discharging, it is coming from 2/3 VCC to 1/3 VCC. Just put those values, and what is T of value? T of value is 0.69 R2 into C, because it is discharging through R2 resistance only. Now what is the duty cycle? Duty cycle is the T on by T into 100. So what is T on? T on time means charging time. Charging time is, we have calculated in the previous slide, that is 0.693 into R1 plus R2 into C. This is charging time. This is discharging time. So what is T on? What is T? T is the total time period, that is T on plus T off, that is charging time plus discharging time here. So it is coming out to be this value, 0.693 into R1 plus 2R2 into C. So what is the percentage D? T on by T. This is coming out to be R1 plus R2 divided by R1 plus 2R2. So this is the duty cycle. Now what is the frequency? Frequency is 1 by T. Just put the value of T here, and the frequency is coming out to be 1.44 divided by R1 plus 2R2 into C, that is in Hertz. Now can we change the duty cycle? Yes, we can change the duty cycle, because in order to change the duty cycle, what we can do, we can connect one diode that is parallel to this R2 resistance. That means when the capacitor is charging, it will be charged through this path. Rest of the circuit is similar. It will not charge through R1 plus R2. Previously it was charging through R1 and R2. Now when a diode is connected parallel to R2, it will charge through this path only, because diode will be providing a least resistance path. So what will be the T on time? T on time will be 0.693 into R1 into C. What will be the T off time? It is discharging through the same path. It is discharging through the same path, so it will not change. So what is that now? T value is TC plus TD, that is this value. So what is the duty cycle right now? This is the duty cycle. So this is the duty cycle of the diode. So with the help of this diode, the duty cycle can be reached. They can be below 50%. Can be below 50%. So previously it was not possible. Now what are the application of 555 timer as Aatablemultivibrator? Aatablemultivibrator could be used in electronic test equipment circuit, and it could produce a wide range of test frequencies, And apart from that, apart from electronic testing equipments, and it can be also be used for making toys, and it could be produced to metronomes. It could be used to produce metronomes. It could be used to produce flash lights, and it can generate, if you can connect it with some speaker at the load end, it can generate some musical tones. Also it can generate some musical tones depending on the frequency. So this is the complete portion.